What would happen if you got into a rocket today and just kept accelerating? No stopping, no refueling, just a constant push at 1g, the same force you feel right now standing on Earth. How far could you go in a day, a week, a month, a human lifetime? Could you reach Jupiter, the next star system, the edge of the galaxy? Because once you commit to never slowing down, space stops behaving the way you think it does. We're about to take that journey, and how far we get won't just surprise you, it will completely shatter your understanding of space, of time, and of what a single human life can actually experience. This is Dark Beacon. And this is what happens when you just keep going. Okay, it's time. Time to start the clock. Or should I say, clocks? Because when it comes to speed and time, Einstein has something to say about it. In his theory of special relativity, time is not an absolute property of the universe, it is relative. And for us, that matters. Because at the speeds we're about to reach, time will be one thing back home on Earth, and something very different here, inside the Dark Beacon rocket. Here's how that works. When Einstein was developing his theory of relativity, he had a profound insight. Until then, space and time were treated as separate things. 3 dimensions of space, the stage, and 1 dimension of time, ticking uniformly in the background. But Einstein realised that space and time are not separate at all. They are woven together into a single 4-dimensional structure, space-time. And motion through space changes how you move through time. When you look at the universe this way, something remarkable happens. The speed of light stops being just a limit. It becomes a kind of constant budget. Everything in the universe is always moving through space-time. The faster you move through space, the slower you move through time. That might sound strange, so let's simplify it. We're going to keep Einstein's space-time, but instead of 3 spatial dimensions, we'll use just 1. A 2-dimensional space-time, completely analogous to our 4-dimensional reality. In this view, time is the vertical axis, space is the horizontal axis. Now remember, we said the speed of light acts like a constant budget. In this model, that means everything is always moving through space-time at the same total rate. In everyday life, we move very slowly through space. We walk, we drive, maybe we fly. But compared to the speed of light, about 186,000 miles per second, that's barely moving at all. So almost all of our motion is directed upward, through time. But as you move faster through space, some of that motion tilts sideways. And if more of your motion goes into space, less of it can go into time. Which means your clock ticks more slowly compared to someone who stayed behind. That's time dilation. That's relativity, the short version. Now, back to the rocket. Now we've done the math, we can start the journey. Day 1. We leave Earth under a constant 1g acceleration. Inside the Dark Beacon rocket, it's cosy, warm, familiar. Because we're accelerating at 9.8 meters per second squared, we feel a steady force holding us in our seats, exactly equal to the gravity on Earth's surface. If you didn't look out of the window, you wouldn't even know we'd left. The moon looms large ahead of us. At this rate, it only takes about 2.5 hours to reach it. Apollo took 3 days. When we fly past, we're travelling at around 87 kilometers per second, and we're still accelerating. Mars is next. On average, it sits about 78 million kilometers from Earth. At a constant 1g, we reach it in just under a day and a half, 35 hours. That's it. By the time we pass the red planet, we're moving at over 1,200 kilometers per second, more than 1,000 times faster than a commercial airliner. And still, inside the ship, nothing feels strange. The coffee rests calmly on the table. The clocks tick normally. Time dilation hasn't started biting yet. Not really. Jupiter doesn't take long either. About 4 days after leaving Earth, we cross its orbit. 4 days to reach the largest planet in the solar system. We're now travelling at over 3,500 kilometers per second, more than 1% of the speed of light. In less than a working week, we've turned the outer planets into a weekend drive. Saturn arrives before the week is out, just under 6 days from Earth. By now, the rings would blur past in a flash. We're moving at over 5,000 kilometers per second, and still accelerating. Uranus falls after 8.5 days, Neptune after just under 11, Pluto after 12.5. The entire classical solar system crossed in less than 2 weeks. By the time we reach the Kuiper Belt, nearly 44 astronomical units from home, it's been just over 13 days since launch. 13 days, and we're travelling at nearly 4% of the speed of light, over 11,000 kilometers per second. Let that sink in. In less than a fortnight, constant acceleration has turned the solar system into something small. And yet, here's the quiet detail most people miss. Our clocks still agree almost perfectly with Earth's. The difference between Earth time and ship time is measured in seconds. For now. Because we haven't been accelerating long enough for relativity to stretch its claws, the solar system was the warm-up. Now, we leave it behind. Proxima Centauri lies just over 4 light-years away, the nearest star to our own. At 1G, we reach it in a little over 2 years of ship time. 2 years. From Earth's perspective, just over 5. Already the difference is measurable. Already time has begun to loosen its grip. We are travelling at over 98% of the speed of light. Space ahead contracts. The distance does not feel like 4 light-years anymore. It feels closer. We don't stop. We don't slow. Vega lies 25 light-years from Earth, a brilliant blue-white star, luminous and distant. At constant acceleration, we reach it in under 4 years of ship time. 4 years. But on Earth, more than 25 have passed. We are now moving at over 99.9% of light speed. At these velocities, something extraordinary happens. The galaxy ahead compresses into a bright tunnel of stars. Starlight shifts blue. The universe itself seems to lean away from us. Space is no longer a vast expanse. It is a narrowing corridor. And still, we accelerate. 5,000 light-years, the near edge of the Great Galactic Bulge, a dense region of ancient stars packed tightly toward the heart of the Milky Way. From Earth's perspective, 5,000 years pass. Empires rise and fall. Ice ages begin and end. History folds in on itself. But aboard the ship? Just 9 years since departure. 9 years to cross 5 millennia. Our velocity is now so close to light speed that the difference is measured in a string of 9s stretching beyond comprehension. The universe ahead is flattened. The journey feels almost gentle. We press on. 26,000 light-years, the galactic centre, a region dominated by a supermassive black hole, Sagittarius A star, surrounded by a glowing halo of stars orbiting in impossible arcs. From Earth's frame of reference, 26,000 years pass. Human civilization becomes archaeology. Languages are forgotten. Continents shift. But aboard our ship, just over 10 years. 10 years to reach the beating heart of the Milky Way. And still, we do not stop. 50,000 light years, the edge of the galaxy. Beyond this, the stellar density thins. The spiral arms trail away into darkness. From Earth's perspective, 50,000 years have passed since launch. But for us, just over 11. 11 years. In barely more than a decade of ship time, we have crossed the entire Milky Way. The galaxy that once seemed immeasurably vast now lies behind us, a luminous spiral suspended in black. And we are still accelerating.
We don't slow down. The Milky Way falls behind us, a spiral shrinking into a luminous disk. For billions of years, it has been our entire universe. Now, it fits inside the nose cone of a golden rocket. Ahead lies Andromeda, 2.5 million light-years away, the nearest great galaxy. At conventional speeds, it might as well be myth. At 1G, it becomes a destination. The black between galaxies thins. Andromeda grows. At first a smudge, then a tilted spiral, then a city of 1 trillion stars suspended in the dark. We do not stop. We do not orbit. We pass through it. Star clouds streak blue. Clusters collapse into arcs of light. Whole stellar populations compress into a narrowing cone ahead of us. Behind us now drift 2 spirals, the Milky Way and Andromeda, twin islands fading into the void. But galaxies travel in families. The local group reveals itself, dozens of galaxies bound together over billions of years, dwarfs, ellipticals, invisible halos of dark matter shaping their motion. We cross them all, still accelerating. The Virgo cluster emerges ahead, thousands of galaxies woven into a gravitational metropolis. What once felt like the entire universe is now a suburb. Clusters link to clusters. Filaments stretch across tens of millions of light years. The cosmic web appears, a lattice of matter spanning the observable universe. Galaxies are no longer islands. They are beads strung along invisible threads, and we are slicing through the web at near light speed. Laniakea unfolds, 100,000 galaxies drifting together in a basin of gravity larger than anything we evolved to comprehend. From here, the universe no longer looks like a sky. It looks like structure, like veins, like something alive. And we keep going. Space ahead narrows into brilliance. Space behind grows dark. And then we approach something subtle. Not a wall, not an edge drawn in stars, but a limit. The universe is not only expanding, it is accelerating. Driven by dark energy, space itself stretches faster and faster. There exists a distance beyond which signals sent today will never arrive. A region where expansion outpaces even light. If we continue long enough, we cross it. The cosmological event horizon. From that moment forward, no message from Earth can ever reach us again, and nothing we send can return. Home does not explode. It does not vanish. It simply falls forever out of causal reach. The Milky Way becomes memory, a shrinking island in a sea that grows faster than light can swim. And still, we are accelerating. If we keep going, galaxies ahead begin to redshift and fade. The cosmic web dissolves into darkness. Clusters slip beyond visibility. One by one, the lights of the universe go out. Not because they die, but because space carries them beyond our horizon. The sky thins. Blue shifts to infrared, infrared to black, until we travel through a universe that can no longer see itself. Racing forever, through a cosmos that is slowly disappearing. And here is where the symmetry breaks. From our perspective, it happens astonishingly fast. Under constant 1G acceleration, it would take roughly 20 years of ship time to outrun home forever. 20 years, less than a human generation. But from Earth's frame, it is not 20 years. As we accelerate, our clocks slow, our motion stretches, our light redshifts. On Earth, tens of billions of years would pass before our signals finally fade beyond causal reach, but Earth would not be there to see it. Within 5 billion years, the sun would swell into a red giant, the oceans would boil, the continents would melt. Earth would not survive unchanged. Within 8 billion years, the sun would collapse into a white dwarf, a fading ember where a star once burned. By the time we slip fully beyond the cosmological horizon, the solar system would be ancient debris orbiting a cooling stellar corpse. Humanity, if it survived at all, would exist only as descendants scattered among the stars, or as dust. To us, the separation feels swift. To the universe we left behind, entire epochs pass before our final light fades. We do not just outrun Earth, we outrun the era that created us. We outrun the star that forged our atoms. We outrun the sky itself.